there it is. Just need to cut all my leads, and I can't wait to give this a test. And I should make a nice little box for it too. Welcome to part 6 of the making of series for the Golden Rovers Discovery 2 LS Swap Kit. In this episode, we're going to be tackling something you've all been asking about. The rover crankshaft position sensor is still there in the front of the crankshaft, facing a reluctor wheel with 58 teeth around it, and that's the setup we inherited from the ACE kit. And a lot of you are telling me, and I am experiencing the same thing, it's very unreliable. It's not very precise. It keeps getting out of alignment. You have to get it just right, and when the temperatures change and the engine heats up, it warps and it stops working properly. So what are we going to do? We're going to get rid of it and replace it with a fake crankshaft position signal that we're going to generate with a computer. You do not want to miss this episode. I'm going to show you everything in every detail of how I get this done. No gatekeeping. Stay tuned. The reason we have the rover crankshaft position sensor at the front of the engine with that reluctor wheel is because the rover ECU needs to know the RPM of the engine to allow you to start it and run it. And it also feeds the tachometer, I suppose, on the dash. But the car will not run without it. The rover ECU will just shut down the ignition and just refuse. Even though the rover ECU is not running the engine, it needs that to allow it to happen. So my idea to replace it is to get like a little microcontroller, like a teensy, and have that generate the crankshaft position sensor signal, which is a 58 tooth signal. And to generate it, what I need to know is the RPMs. So I need to know how fast the engine is spinning. The rover side doesn't need to know exactly the position of the crankshaft, ironically. It doesn't need to know exactly where the engine is. It just needs to know how fast it's going. So I'm thinking, instead of converting the crankshaft position sensor signal from LS to rover, which would be hard, right? Because the LS is using a 24x signal, which is a completely different waveform. Instead of trying to analyze that and convert that to a 58x signal, what if I could find the tachometer signal on the LS side and just read that to get the RPMs and use the RPM value to generate my 58x signal. So over here I've got a picoscope, which is a PC-based oscilloscope, and I've got my laptop, and I'm going to set it up to probe hopefully find the tachometer signal and see what that looks like. So I've got the laptop set up, the picoscope, and the GM LS engine. And I read on the forum that probably this white wire coming from the red connector is the tachometer signal. So it's very convenient that it's right there. I'm going to probe that wire and see if I come up with anything. I put a needle probe in that white wire, and I've got also the probe, a ground reference on the computer. Hopefully the computer is grounded, right? And now, of course, I'm not seeing anything yet, but when I turn on the engine, hopefully we'll have a tachometer signal. It looked like we did something there. There was a signal that was going from 0 to 12 volts up and down, and it seemed to be maybe telling us what like a square wave telling us the RPMs of the car. Because I'm holding the camera, I couldn't hit the throttle and see if the RPMs increase if the waveform changes, but I'm gonna get a tripod and do that. I'm gonna go and hit the throttle after I start this thing. Feels silly now. My LS wiring harness came with a spool of, extra wires to nothing, and one of them is, go figure, tachometer, the white wire. So right here, accessible, easy. With the engine off, I can analyze the capture and pick up the frequency. For example, it says it's 25 hertz. That means 25 up down per second. If you multiply that by 60, you get the number of up down per minute, and it's 1500. But I think it's counting, I'm not sure how it's counting it. I think it's doubling it because the RPMs are 750. So it's counting all the vertical bars when it should be counting every other. Something like that. So I've got my running stock D2 here. And I need to figure out which wires hook up to the crankshaft position sensor. So I know which wires to probe. So onto the shop computer. I've got the Rave here, the shop manual. And it says connector 3 is 52 pins. And 32 is a CKP sensor signal. Analog 0 to 300 volts peak. Very high voltage. See, this is why it's a very sensitive sensor, because at high RPMs the voltage becomes very high. And that tone wheel is not necessarily precise enough. We also have pin 45 sensor earth. I assume that's like the ground. And the sensor signal earth reference. So okay, that's the ground reference, number 46. So we have three pins, but I think 2 of them we care about, the signal and the earth. So this is the Bosch ECU from the rover, and I think I found my connector. 1, 2, and 3. Connector 3. 52 pins. So this is it. So now I need to find the correct pins. Thankfully they're numbered 1 through 13, and then 14 through 26, etc. So I forgot what pin numbers I was looking for, but I'm gonna go look at it again. I took the connector apart and I worked out that pin 32 is this dark grayish one, so I back probed it, and 46 is this orange wire coming in, so back probed that. And now I'm going to put everything back together, and we're going to read our signals from these alligator clips. Okay, I got my probe attached to my probe and my ground references. So laptop is here. Let's do this. Okay, engine's running and we have something. Let's calibrate. Oh boy, here we go. Yeah, that's probably it right there. That's our crankshaft position sensor signal. So, yep. You can see there's one big tooth missing. That's where that is. And I'm guessing we got the 58 tips between those. This is the signal we need to generate here. So it's like not really a sine wave, but almost. And then this shape. Interesting. Let's see if it increases with RPM. It does change with the RPMs. Look at this. Kind of funny, isn't it? Okay, let's save that. So, I've collected the data I need. I know what signal I need to generate, and I've ordered a teensy microcontroller, which I'm going to program to generate that, right? But in the meantime, what I can do is I can use my picoscope. It has a signal generator output, and I can generate a signal and test to see if that works. Because I'm not 100% confident that this will work. The variable reluctance sensor, that is the crankshaft position sensor, it varies in voltage wildly. As it generates its own AC current. So as the RPMs go up, that tone wheel spins faster and generates a current in the sensor. and it can go up to 300 volts. That's what the input on the rover ECU is rated for. So obviously I can't generate 300 volts out of a teensy microcontroller, and I don't think I should. I'm banking on the idea that hopefully the rover ECU can recognize any wave, even if I put in like a sine wave or a square wave. What I think it's doing is it's counting how many times the wave crosses zero. So this is 0 volts in the middle. I think what the rover ECU is doing is counting how many times does it cross. Does it go from positive to negative, right? And so if that's what it's doing, then I can use a square wave or a sine wave or something really simple. And maybe the amplitude doesn't matter. Normally the amplitude goes up with RPMs, but as long as the rover ECU doesn't care about that, I can get away with making a simple low voltage sine wave or something. But to test that theory, I'm going to use the signal output of this and hook it up to the crankshaft position sensor plug, and I'm going to feed that sine wave or square wave to the rover ECU as if it was a crankshaft position sensor, and we'll see if the car starts and stays running. Here I am generating a very similar signal. It goes from negative 0.8 volts to positive 0.8 volts, and it's 800 hertz, which is the frequency that my capture was. It is a sine wave. I'm going to try feeding this to the rover ECU and let's see if it starts and runs. Okay, I'm still generating that signal, but now it's hooked up to there, and I've got the ground reference, and let's see if it starts. That's a no. The reason it's not working is I forgot something kind of obvious. I tried all the wires. I think the problem is it's not just enough to generate a sine wave. I need to skip 2 teeth. Every 58 teeth, I skip 2 to make 60. Right? There needs to be a gap to tell the ECU what angle it's in. So I think the ECU is just waiting for that tooth gap and not getting it. And that's why it's just not starting at all. So I don't think I can do that with this picoscope. I don't think that's a feature. So I may just have to wait until the teensy computer comes in. Well, actually, it turns out you can draw your own wavelength to output. So I drew a 60 peak square wave, generated that, and knocked down 2 of the peaks at the end, and cycling that. And I think I have something that could be workable. So I'm going to try this again. Okay, so I've got my square wave going just a little above 0.8 to negative 0.8. And let's try it. There it is. We did it. We did it. So, looks like a square wave with 2 peaks knocked down. And the rover ECU is happy. Also fun, with the engine off, I can increase the frequency here and check that the tachometer reacts. So I'm going to increase it. Increase it. Increase the frequency some more. Yeah, the tachometer is reacting as expected to, to my artificial square wave. But yeah, at least we know that amplitude doesn't matter. The exact shape of the wave doesn't matter. You just have to have up and down of some sort and skip 2 teeth out of every 60. And ta-da! So this is the teensy microcontroller. It's a little computer like an Arduino, and you plug it in through USB, and as soon as it gets power, it immediately runs the program that is on it. So there's no startup delay, it just bam, runs the program. And it has a bunch of pins that can be used as inputs to detect a signal or outputs to generate a signal, among other many functions. But that's all we need to know for now. So I just plug it into my PC, and I can program it and upload programs to it from here. And because I have my picoscope hooked up, I should be able to test everything from here before I take it to the vehicle. So in the picoscope, my setup is I'm going to set it to generate a signal output. We're going to say 12 hertz, which is about 700 RPM. This is generating our tachometer signal like the LS gives us. So about 12 hertz should be a good start there. And we're going to change that to a square wave. So we're generating a tachometer signal out of here. So I'm going to hook that up to pin 22, which is where we're going to measure from. Only one crucial difference is that the LS tachometer is a square wave that ranges from 0 volts to 12 volts. But we cannot feed 12 volts into the teensy. It's a tiny little computer that can't read. It can't take more than 3.3 volts. So when we hook this up from the vehicle, we're going to use one of these. It's a little voltage divider. It literally divides the voltage by 5. So we're going to get like 2.4 volts instead, a 2.4 volt square wave. I'm going to put that there between the pin and the tachometer. And so we're going to be able to read that safely. But since we're generating a 2 volt square wave from the picoscope right now, we don't need this for now. We only need it in the vehicle. I'm going to output the crankshaft position sensor fake signal from pin number 2. So I'm hooking that up to the picoscope as well so I can monitor it. This is my code. I'll go over it quickly. I'm defining my output pin as 2. I'm starting with an RPM of 500 by default. I'm going to count how many teeth I've generated. You'll see there. And I'm going to measure the frequency of the incoming tachometer signal. So that's actually the first thing we're going to do. We're going to set up the frequency measure library, which is provided to us. So that's great. I don't have to do any work. And in our loop function, we're going to see if it has measured the frequency. And so we're going to read that. And we're going to take the sum of a few of them. We're going to add up 4 frequency readings and average them. So once we have a reading, we'll average it and ask the library to just give us a frequency value in hertz. And because we have 60 teeth, to get the number of teeth per second, we just have to multiply the frequency of the tachometer by 60. But because there are 60 teeth, and coincidentally there's also 60 seconds in a minute, the frequency of the crankshaft position reluctor teeth is the same as our RPM value. So you can put that straight in there. So we're measuring the RPM from the tachometer. And if the RPM value is something crazy over 10,000, then we're going to default back to some value like 700. This might change. These are just placeholder numbers for now. So we successfully read the RPM from the tachometer. And the next, and this is it. It's not a lot of code, but we're still in our loop function. And what we're doing is we're first determining the interval. So this is the interval between pulses of the crankshaft position sensor. So 1 million microseconds, which is 1 second. 1 second divided by the RPM, which is also the teeth per second. So that's our interval between teeth, right? So remember we had our tooth count variable that starts at 0. So if we're in the first 58 teeth, so if the tooth count is smaller than 58, then we're going to set our pin to high, means pulse upward. We're going to wait half an interval, set our pin to low, which is down, and wait another half an interval. And we're making a square wave that way. And we're going to loop and do that over and over and over, 58 times. But if we're above 58, then we're not going to do that. We're just going to wait an interval. And we're going to do that for teeth number 59 and 60, which is going to simulate our 2 missing teeth, right? And so we're incrementing the tooth count in this loop. And what this says is if the tooth count reaches 60, reset it back to 0. So basically we're counting our teeth 1, 2, 3, and we're doing a square wave pulse for each of our teeth. But for number 59 and 60, we're skipping that and just waiting. And then we're starting over. So I'm going to upload that to our teensy, and we're going to see what happens. So obviously I skipped the part where there were tons of bugs and I just, fixed them. But I have my working code. So here is the reading out of my pin number 2 where I'm generating the signal. And this is the signal we want. It's got 58 teeth and then 2 missing, and it keeps going. I'm using this website, Falstad, to simulate our situation here, where I'm generating a square wave out of here. And I've experimenting with different ways to shift this downward so it's centered around 0. You can use resistors and capacitors, but I found one very simple way. This is what I've come up with. Imagine this is the teensy generating a 700 Hertz square wave. This is a 220 ohm resistor just to protect the teensy from overcurrent. And this here is a transformer, a 1-to-1 transformer. The transformer is 2 coils wrapped around the same iron core. So the purpose of a transformer usually is to change the voltage, to go from one voltage to another. So by changing the ratio of one coil to another, putting more coils on one side than the other, what happens is when you apply one current to one side, if it's an oscillating, alternating current, it will induce another current on the other coil. And the voltage will be different if the coils are at a different density. So applying an alternating current on one side induces a current on the other side. It only works with an oscillating current. If you were to apply just a direct current, fixed 5 volts to one side, it would do absolutely nothing on the other side. It's just 0. But say we were to put in a square wave on one side that is from 0 to 3.5 volts, oscillating up and down, it will create the same. In our case, we're using a 1-to-1 transformer, meaning it's the same coil. So we will induce pretty much the same square wave on the other side, except it'll be centered around 0, 0 being the reference of one of these 2 prongs. So you put your positive on one and the negative on the other, and then it'll show you a wave centered around 0. Because transformers only let in alternating current. They don't have a DC offset. And the nice thing is that since these 2 coils are separate, this also isolates the teensy microcontroller from the ECU. And this isolation provides some safety from accidental overcurrent or some surge happening and damaging the computer. If we this is our square wave generated by the teensy. If we put it through the transformer, it comes out like this, as an up and down. The square ends up slightly modified, but it goes up and down around 0. And so that's what I have here. This is our 1-to-1 transformer. It's got one coil on this side with 2 prongs and another coil on the other side. It's super simple. Right, so that's what that looks like. Going up and down, a bit choppy. And we've got our tooth skipping going on there. And now for comparison, I'm going to open a capture of the real crankshaft position sensor that we measured. And this is what it looks like, going up and down around 0. And once in a while, you find our missing teeth. So from this to this, let me adjust the scale. Close enough. I mean, obviously it's not a smooth wave, but I don't think the ECU cares. It just cares that we have the correct number of 0 crossings and skip teeth. So I think we have our setup. If I'm confident enough, I'm going to take this computer straight to the vehicle and see if it'll start and see if the tachometer works. I got my crankshaft position sensor wire coming through here. I'm about to snip off this connector and hook up the pink and the black to the other side of the transformer, which is where our fake signal is going to come from. It looks pretty sketchy, so I'll walk you through it one more time. This is our tachometer signal coming from the LS, and a ground goes into a voltage divider So it comes, because it comes in at a 12 volt square wave, comes out a 2.4 volt square wave. We've got the signal wire going to pin 22, our input for the teensy, and the negative going to the common grounds here. Ground goes to ground. Then our pin 2, our output signal, is brown, goes into the breadboard to one side of the transformer, and the other side is grounded. Or the other pin, I should say. And the other pin is grounded. And then on the other side of the transformer, we have, directly stabbed into the breadboard, the crankshaft position sensor wires. Pink is our signal, black is our ground, and it's isolated from the teensy through this transformer. So that's the setup. Let's try to start it. Awesome. Not only does it start, but the tachometer works fine. And this is all thanks to the little teensy computer. I think we did it. I'm back at the computer, back here, because it's really exciting that this works, but I'm not totally done yet. I need to add a few things for electrical safety. First is a 220 ohm resistor between the teensy output and the transformer, mostly to protect the teensy from an overcurrent. Second thing I'm adding is a 10 kilo ohm resistor between the two prongs of the transformer on the ECU side. This is going to the ECU crankshaft position sensor wires. This 10k ohm resistor across acts as a shunt. It's a low resistance path for current to go through. So if there's an overcurrent, it'll basically burn off through there, as I understand it. Potentially I could add a capacitor to smooth this out, and smooth down the peaks, but it may not be necessary if everything works fine. And another thing, putting a capacitor across the secondary coil of the transformer going to the ECU attenuates the signal, makes it look like sharp on the edges. Here's without the capacitor, and with the capacitor. It's just like smooths out those sharp edges. Here's a test at 6,000 RPM. This is without the capacitor. With the capacitor, with, it's definitely a lot smoother, but it does attenuate the signal slightly below 1 volt, which I don't know if that might be too aggressive. I might have to tune my capacitor and resistor values. So I was experimenting here. So, and I landed on 47 nanofarads being a good compromise, or it's not attenuating too much. So if I take it out, that's our wave. And if I put it back in, it's just smoother without dropping the amplitude too far. I'm also deciding between the transformer and the ECU, I'm going to put two 47 ohm resistors on the plus and the minus going into the ECU crankshaft position sensor wires, just as an overcurrent protection. And I'm choosing two on the plus and the minus to keep it balanced, because it is a current that is equal in the positive and the negative. Another thing that would be cool would be to add an RGB LED that would be visible on the outside of the box that I packaged this in, so you can see that this is turning on, receiving power, and it has a status. I'll probably make it like a green light if everything's okay, a red light if there's a problem, a yellow light if it's just like waiting, that sort of thing. So it's been a few days and the circuitry has evolved, but it is functionally the same. Power comes in 12 volts, goes through a buck converter to 5 volts to power the computer. Tachometer comes in, goes to the computer, and CKP, crankshaft position output, comes out from here. And really all these resistors and capacitors are just there for safety. So instead of going through it here, which is kind of messy and hard to understand, I made an actual schematic. And let me show you what's going on. So I added an LED to communicate status to the user. So it'll be blue when it's waiting, green when it's generating crankshaft position sensor output, and red if there's an issue, like the input is wrong. So the circuitry for that LED is really simple. Each of the legs of the LED need a 220 ohm resistor per the data sheet, and they go to 3 digital pins on the teensy computer, right? Easy peasy. Then we've got our 12 volts in. That goes into the buck converter, comes out, and powers the 5 volts of the computer here. Boom. Next we got tachometer. Tachometer is one wire coming in, and it goes through a voltage divider. For that we have a 30 ohm and 7.5 ohm, 30 kilo ohm and 7.5 kilo ohm resistors, and we connect to the middle of those two resistors, and that is going to cut our voltage down to a range that is okay, because the tachometer comes in at 0 to 12. So this will cut it down to 0 to 2.4, I think. So we've got a shunt resistor to clean up any noise from the signal, and then 1 kilo ohm for extra protection coming out. So our fake crankshaft position sensor signal comes out of the computer, 220 ohm resistor, and it goes through a transformer to offset it down so that it's centered around 0 volts. Then 10 kilo ohm resistor and 47 nanofarad capacitor will smooth out that signal, and we put 247 ohm resistors for safety. And that's it, except I decided to add one more thing, which is, if you remember from part 1, we had the ACE box, which converts the rover vehicle speed sensor to a signal that the GM ECU can understand. So VSS for the GM computer. And I decided, hey, why don't I integrate this into my circuit board, add it to the schematic? So I did it. Very simple. Rover VSS comes in, goes through a 1 microfarad capacitor. Then there's a 1 mega ohm resistor, and from the legs of that resistor comes out the GM VSS positive and negative. So this will be integrated in there, and I can get rid of that that box from ACE because it'll just be integrated into my board. But these are all the same components laid out on the printed circuit board with through holes. So I'm going to solder my own stuff so that I can take stuff out and experiment. Of course, I decided to have some fun with it, put the logo in there, LS swap everything. We've got a little disco and some trees. I've got the 3 amigos hiding in there for good luck. And yeah, and you can even go and look at a 3D rendition of the circuit board. So that should make it even more clear what's going on. Our teensy computer will get soldered on there. It will, I've annotated everything. So we've got our tachometer going through a voltage divider, going to a pin on the computer. We've got the rover VSS, capacitor, resistor, and out to the GM VSS signal. Got our LED there. Crankshaft position sensor comes out of the computer, goes through the resistor, goes through the transformer. We've got that capacitor, resistors, and there's our fake crankshaft position output. And then power in comes in, goes through the buck converter, and powers the computer. That's it. There have been some code changes as well, so I want to walk you through them. First of all, a circular buffer of size 5, where we are going to store RPM values. And that way we're going to take the average of the last 5. I've changed the way that I measure the incoming square wave for the tachometer. I am using interrupts, which means what it's doing is saying, oh, when the pin detects that it's rising, going upwards, called call a function, handle pulse. So I'm going to detect that. I'm going to detect when the current goes up, and it's going to call a function. And I'm going to check the time between each function call, and that's going to give me the frequency of the tachometer. So we've got our LED now, so I'm going to set it to blue for standby. We're waiting for the tachometer to show up. Now I have my function get RPM, which takes the average of all the RPM values we put in the buffer. We've got add RPM, which puts a new value in the circular buffer, right? So it just keeps adding values and then looping back around the buffer. We've got read RPM. This function is called on a loop, and it is the one that will calculate the RPM. So we've assigned a pin that when I ground it, we're in test mode. Test mode means we're not going to read the RPM values from the tachometer. We're just going to skip that and set it to a fixed 1000 and set the LED color to purple to show that we're in test mode. And that's if there's an issue with the tachometer, we can just bypass that and at least send a value to the rover computer that is plausible, and at least it keeps the car running. So test mode is handy. Otherwise, if we haven't had a pulse from the tachometer for a whole second, then assume the car has turned off, and set the LED back to blue for standby, and clear the circular buffer by filling it with the default RPM value, which is 100. So now, if there's been a new reading, meaning new reading, so handle pulse is the function that gets called when we detect that the current is going upwards. So we detect the up part of the square wave. We store the current time. We see how much time has elapsed since the last time this function was called, and we mark that we've had a new reading. So if we've had a new reading, then we take the elapsed time, and as long as it's bigger than 0, which it should be, we calculate the RPM from the elapsed time. Because it's rotations per minute, we have to multiply by 60, and because the elapsed time P is in microseconds, when we have to multiply by 1,000,000. And also, for some reason, the LS tachometer pulses are doubled up. So for each rotation of the engine, it gives you 2 pulses. So for example, at about 700 RPM, we'll get a 25 Hertz pulse, when really I was expecting a 12 Hertz pulse. So we have to multiply by half to get the real RPM value. So if the new RPM is less than 10,000, which means it's valid, then add it to the circular buffer and set the LED color to green, meaning we have success, we're correct, we're successfully reading the RPM. However, if the new RPM value is bigger than 10,000, that means it's definitely something's wrong, so mark red for error. And yeah, that's how we read the RPM from the tachometer. And this is our main loop. This function runs continuously. We check if we're in test mode first. We read the RPM, that's the function we went through above. And now we get the RPM, which is calculating the average of all the RPM values in the circular buffer. So if it's bigger than default RPM, meaning we actually, bigger than 100, which means the car is actually running. If that's the case, I'm going to calculate the interval between the teeth. So there's a funny coincidence happening here, because there are 60 teeth on the reluctor wheel, and there are 60 seconds in a minute. The RPM is also the number of teeth per second. It happens to be the same number. So to get the interval between the teeth, we divide 1,000,000 by the RPM. So we do have 60 teeth, but we skip 2. So if we're in the first 58 teeth, then put an upward spike in our output pin, wait for half an interval, then drop, and then wait for another half an interval. However, if we are in one of the pins that we're skipping, so in this else statement, we don't do anything because in the last time we put it on low. So instead we just wait a whole interval without doing anything. And we increment our tooth count and loop it at 60. So that's how the code works. Let me know in the comments if you enjoy looking at code or if you would prefer that I never do that again. So it's been less than a week, and this is exciting. The printed circuit board just arrived. Check that out. There it is, with our logo, our disco, the three amigos hanging out. Now all I have to do is solder in all the components. There it is. Just need to cut all my leads, and I can't wait to give this a test. And I should make a nice little box for it too. Over here I've got these terminal blocks that are push in. You push this button, then you put your wire in, and then you let it go, and then there's a spring that clamps your wire. So it's really easy. So I'm at the vehicle, and I'm gonna hook this up. So let's see, for 12 volt power, any 12 volt source will do, but my BP Automotive wiring harness comes with a bunch of pink wires that are supposed to be for fan relay control, for electric fans. And these are 5 amp fused wires, so they supply 12 volts, that'll be perfect. So, to hook it up, I press down on the button, insert the wire, and let go. And it's in there good, and it's under spring tension. Now for 12 volt ground, I hooked up a wire to the wall there, and I'll show you a picture of that. And same thing, I'll throw it in there. There we go, that's 12 volt ground. Next up is crankshaft position sensor, negative and positive. Okay, so that's these wires. Just as a reminder, what I did here is I snipped off the connector that goes to the crankshaft position sensor on the engine, the rover crankshaft position sensor, of course, and I routed the wire back through the firewall to come out of here. So the pink one is the positive, the black one is the negative. So we're going to hook that up. Crankshaft position positive, boom, there, crankshaft position negative, done. Next is the LS or GM tachometer wire. This is a white wire coming out of the PCM, and on my BP Automotive wiring harness it was labeled tachometer and ready to go. So that makes it very easy. LS tachometer, boom, done. Now the 3 remaining ports are VSS, vehicle speed sensor rover, and these 2 are vehicle speed sensor LS, positive and negative. So what these are is, for those of you who have the ACE kit, it came with a little box like this that contained this circuitry, and all it did was it connects the throttle position sensors together. There's no conversion there, and it has a little resistor and capacitor to convert the rover vehicle speed sensor to GM. This is to tell the GM, the LS PCM, how fast the car is going. It needs to know. So what I did is I transferred that circuitry here. So what we'll do is we'll connect the throttle position sensors together and solder them. And then the board here will take care of our VSS from now on. So I'll be able to get rid of this ACE box. Okay, that's done. So the rover, let's see. So the rover VSS is this red wire, which is wired, comes from, this is done according to the ACE kit instructions, comes from this pink wire on the rover ECU. So we tap into that. The GMLS VSS is these two braided wires, green and red, that we've, according to the ACE instructions, routed back through the firewall to here. So we're feeding VSS data to the GM computer. And then, so this replaces that black box from ACE. And the only difference with the black box from ACE is that we connect the throttle position sensors together right here. So this is the rover one from the rover wiring harness, and this one, this blue thing, goes, and I've tapped the throttle position sensor wire out of here. So yeah, simple as that. So now we don't need the ACE black box anymore because I've integrated the circuit into here. Okay, now we got to try and see if it works. Beautiful. We've got a green light, so we know it's happy. Green is good. The tachometer seems to work. So that's a good sign. Looks like our board is fully functional. So I think the only thing left to do is to make a nice box for this so it can be mounted neatly. As soon as this video is posted, I will list this for sale on our website, goldenrovers.com. For those who have an immediate need, for example, those who have the ACE kit and they're having issues with the rover crankshaft position sensor and the reluctor reel not aligning, you can buy this board and replace it. And for those who are doing an LS swap with a GM transmission, this could still be helpful if you want to try and keep the traction control working. You will need to keep the rover ECU happy and feed it crankshaft position data. So you can use this board for that, and you could just ignore the VSS part of it. Yeah, and that'll keep the rover ECU happy. It'll make the tachometer work fine. So it could be useful in those cases. So yeah, it'll be for sale, backed by our warranty, just like anything else. If there's an issue, we'll fix it or replace it. So to make the box, I can conveniently export the entire circuit board as a 3D model. And so I was able to make a top lid for it and the bottom. The top goes in like that, and I just need some little screws to put in there, and we're good. So that'll do it for part 6. Mission accomplished. We got rid of the crankshaft position sensor and replaced it with this board. So if you have a need for one of these boards right now, they are up for sale on goldenrovers.com. I have a link in the description directly to the product so you can get one. These could be useful to you if you have the ACE kit and the crankshaft position sensor is being annoying and you can't get it right. Or if you are doing your own swap with a GM transmission, but you're trying to keep the traction control working by keeping the rover ECU happy and running, you might need one of these. You could use one of these to feed it a crankshaft position sensor signal, and it'll work. So anyway, that was part 6. In part 7, we're going to start working on some details and finishing touches. Stay tuned for that. Thank you for watching.